Welcome students to the next lecture of digital communication. So today we will discuss about optimum receiver for binary data transmission. So far you have studied that given any signal we can represent them geometrically on a signal space. Okay. So let's say if you have two signals in time domain S1t and S2t, then if you can define two orthonormal basis functions phi1t and phi2t such that they have this property that if you take the dot product of them, then they are 0, and if you take the norm, then that is 1. Then in that case you can represent the signals S1t and S2t as a linear superposition of phi1t and phi2t with these coefficients. Okay, and if you can do that, then these coefficients are nothing but they are the projections of the signals onto the phi1 axis and the phi2 axis, and then you can define a two-dimensional space having two axes phi1 and phi2, just like your x and y axis in Euclidean coordinate geometry. And then you can represent these signals as dots in this space, where let's say this is your S1 and this is your S2, and the projection of S1 on phi1 is given by S11, and on phi2 this is given by S12, and similarly for S2 the projection is given as S21 on phi1 and S22 on phi2, and you can calculate the projections easily by correlating with for the phi j's like this. So this is how you can represent the signals as dots in the signal space, or as a vector that connect these dots from the origin with the direction towards these dots. So they can be represented as vectors and also as points in the signal space that is defined by these two dimensions phi1 and phi2, where phi1 and phi2 are orthonormal to each other. And then given S1 and S2, how to choose orthonormal functions phi1 and phi2 to represent S1 and S2 exactly, this question can be answered by the Gram-Schmidt orthogonalization, which we also covered in our previous lectures. So you can have phi1 which is along the signal S1, and then if you calculate the projections, then you can find out phi2 dash using this formula, and then you can normalize phi2 dash to get phi2, and then if you have multiple signals you can extend this and then you can find out all the required dimensions of the signals. So you can generalize the Gram-Schmidt formula by this method, and then you can calculate all the phi k's. So in most cases you will see that two dimensions phi1 and phi2 are enough, but Gram-Schmidt will give you exactly the number of dimensions that you need to represent a set of signals. So now in this lecture we will see that the noise that you have in your communication systems, which is a random process, that can also be represented as a combination of these phi i's. Okay, so you can write the random process of the noise Wt as a sum of these phi i's t's with some coefficients wi, and these wi's are calculated like this, and these are random variables, and they follow the same statistical properties of the random process wt. So if wt is zero mean and white, then you can show that the mean of these coefficients wi's are also zero. Okay, if you do this math, then you will find that the mean is also zero. If you replace wi's with this expression, and then if you separate it out, then you will find that inside this integral you have this expectation of wt, which is 0 because wt is 0 mean, so essentially you will get 0 as the expectation of wi also. And if you take the correlation between wi and wj, then also you can show with some mathematical manipulation that this value will be n0 by 2 if I is equal to j, and it will be 0 if I not equal to j. So where n0 is the power spectral density of your zero mean white noise. So what does this mean? This means that these coefficients wi, denoted as w1, w2, dot dot dot, are zero mean and uncorrelated random variables. Okay, so if they are separate, I not equal to j, then they are uncorrelated, and the autocorrelation, which is the case when I equal to j, is n0 by 2. So if wt is not only zero mean and white but also Gaussian, then these coefficients w1, w2, etc., these are also Gaussian random variables, and they are statistically independent. So we will use these properties while analyzing our signals in digital communication in the presence of noise. So let's say if you have a signal SIT, so you saw that in case of a binary transmission you are sending S1 when there was a 0 and S2 when there was a 1, right? So let's say you have a general signal SIT where I will be 1 if 0 is transmitted, or 2 if 1 is transmitted. That can be represented as SI1 times phi1t plus SI2 times phi2t. Okay, because we are representing the signals geometrically, so we have already established these concepts in the previous classes that we can represent any signal in time domain as a dot in the signal space if we can find out phi1 and phi2 using Gram-Schmidt formula. So your SI is getting added with the noise WT, okay, and you are receiving a signal at the receiver as RT, which is SIT plus WT. Now your SIT is written like this, and your WT can be written as you saw in the previous slides, that it can be also written as a superposition of all these phi i's. So you can write WT as W1 phi 1 t plus W2 phi 2 t plus W3 phi 3 t and so on. So now if you collect the similar coefficients, so the first term will be SI1 plus W1 times phi 1 t. The second term will be SI2 plus W2 times phi 2 t. And from the third term onwards, you have just the noise. Okay, W3 times phi 3t, W4 times phi 4t, up to infinity. So, so then you can write this as R1, this as R2, and this is R3, and so on. So these are the different components of the received signal. Let us imagine that your RT can be expressed as R1 times phi 1t, R2 times phi 2t, R3 times phi 3t, and so on, where the first two components contains the signal, because the signal is only two dimensional, represented by phi 1 and phi 2, and the remaining components from R3 onwards contain only the noise. Okay, so this is it. So R1 is your signal plus noise, R2 is signal plus noise, and then from R3 onwards these are only the noises. Okay, so so note that Rj for j equal to 3, 4, 5, etc. does not depend on which signal was transmitted. Okay, so given that your received signal, it can be expressed as a combination of these components R1, R2, etc. You can observe these variables R1, R2, R3, R4, and you can make a decision based on these observations. Okay, so if you remember when we were doing the discrete memoryless channel in the very first or second lecture, we were observing the variables at the output or the output alphabet, and we were trying to make a decision based on our observations of the output what was transmitted. Here also, once we can represent the time domain received signal RT in the form of its components R1, R2, R3, and so on, then we can just observe these components of the received signal, and then we can make a decision of what was transmitted, what were the components of the transmitted signal based on this, just in the same manner as we were doing for the discrete memoryless channel. Now the criteria here is to minimize the bit error probability as usual. So this is the fundamental requirement of the communication system. So let's look into this problem from the signal space perspective. So consider that you are interested only with the first n terms, okay, of the received signal, R1, R2 up to Rn. Okay. Ideally this should run to infinity, but we are only observing the first n terms. So in that case you need to partition the n dimensional observation space into decision regions. Okay, so let's simplify things a little bit. Let's first consider that this n is equal to 2. Okay, so let's focus on a two-dimensional space and try to understand this problem, and then you can extend easily to n-dimensional space. So if from the two-dimensional perspective, let's say we have entire observation space R, which is this outer boundary. Let's say this is your observation space R, and you partition this observation space into two different regions. So R1 is one region and R2 is another. So let's say this is R2. Okay, so whatever is shaded gray here, and the white spaces are R1. Okay, so let's imagine that your received signal R has two components. Okay, R1 and R2. Okay, so if and you can define the received signal in terms of these two components. Okay, so it will be R1 phi 1, let's say, plus R2 phi 2. Okay, so if your if your R, which is your received signal, which is represented by these two components, so basically if you imagine that this space is a two-dimensional space, then any point in this space can be represented as R1 and R2, like the two coordinate values. Okay, so if based on your R1 and R2, if your signal falls here, within the region capital R1, then you decide that a 0 was transmitted. But if it falls here within capital R2, then you decide that a 1 was transmitted. Okay. So the rule is very simple. So your received signal R has two components, R1 and R2. Okay, and these are basically your signal. Okay, signal I1 plus the noise W1, and this is the signal I2 plus noise W2. So I is, if it is binary, I can be 1 or 2. So basically R1 is either S11 plus W1 or S21 plus W1, and your R2 is S22 plus W2 or S12 plus W2. Okay. So based on this, if your R1 and R2, after you calculate these, falls here, either here or here, then say you decide that your signal was S1 or 0, and if the opposite happens, then you decide that your signal was S2 or 1. Okay. So now extending this concept, if I want to now calculate the probability of error, okay, so what will we do? So let's say your probability of error is nothing, but you decide a 0 but actually a 1 was transmitted, or you decide a 1 but actually 0 was transmitted. So this is the two different ways with which you can have a error. So this means let's say 0 decided, we term this term as 0D like this. So this means probability of 0D and 1T. 1T means 1 was transmitted, plus probability of 1D and 0T. So if you break these two terms in terms of the conditional probabilities and the probability of transmission of ones and zeros, then you can have this term. So this is basically probability of 0 decided given a 1 was transmitted times probability of 1 transmitted plus probability of 1 decided given a 0 was transmitted times probability 0 transmitted. Now these two probabilities, probability of 0 transmitted and probability of 1 transmitted, let's assume that these are known. Okay, so this is equivalent to the a priori probabilities that you learned when you were doing discrete memoryless channels. Okay, so basically let's imagine that probability of 0 transmitted is called P1 and probability of 1 transmitted is P2. So I can put these values here. So P2 is here and P1 is here, and the conditional probabilities can be defined as this. So conditional probabilities are nothing but the integral of the conditional PDFs within region R1 and region R2. So so probability 0 decided given 1 transmitted. This means that your received signal is falling within region capital R1. So that was the rule, right? If your received signal falls here, then you decide a 0. So probability of 0 decided means that you are observing all the points within the region capital R1, and you are basically integrating the PDF, the conditional PDF of the received signal given a 1 was transmitted based on your observations at region capital R1. Similarly here, probability of 1 decided given 0 transmitted is only happening when you are observing all the points that are falling in region R2, because that was the rule. If your points fall here within R2, then you decide a 1 was transmitted. So you are deciding that a 1 was transmitted, but actually a 0 was transmitted, and that's why it's an error. So let's imagine that you are observing the points in the region R2 for this particular term. Okay. So so this is what we get. Okay, up to this. So far so good. Okay. So so let me say it again. Probability 0 decided given 1 was transmitted is only happening when you are observing your points at R1. Okay, and if 1 was transmitted and still your received signal is falling within R1, forcing you to make a decision that 0 was actually transmitted, is giving you the error. Okay, so 1 was transmitted, okay, actually, and then your received signal R is falling in the region R1. Okay, then you are deciding based on this that actually 0 was transmitted, but actually 1 was transmitted. So these two are mismatching, and therefore you are making an error, right? So that's the point here. So you are observing all the points that are falling on R1, and based on the rule that you have set, whatever falls in R1 is decided as 0. You are deciding them as 0, but if it was an actual 1 transmitted, then it's a case of error. And this is written as the a priori probability times this integral over all points in R1 plus the a priori probability P1 times this integral over all points in R2. So now you can make a little adjustment. So you can write R1 as R minus R2, because whatever is falling in R1 is the points that doesn't fall in R2. So these two spaces are mutually exclusive. Okay, so you can write R1, the set R1, as the total observation set R minus the observation set R2. Okay, so this integral is just adjusted with this set. Okay, so now this integral can be further split into the same integral over R minus the same integral over R2. So R minus R2 can be separated out. Okay, so so let's say this part can be written as two integrals. One is over R with the same functions inside, minus the other over R2 with the same functions inside. Okay, and then this part that is over all the R is here, and over all R2 this part is adjusted with the next integral which was also within R2. So this integral minus this integral. Okay, and then everything is taken together over R2. Okay, so now if you see that this integral is over the entire observation space, so if you are integrating this PDF over the entire observation space, then this will give you 1. Okay, so this entire integral will be P2 times 1, so that is just P2. Okay, plus this one which is as it is. So now let's see what is happening. So let's make it clear. Let's make this slide a little bit clearer. So now the probability of error, we started from here and we reached at this expression. So let's analyze this expression. So the probability of error is basically P2, which is a fixed term. That was the a priori probability of sending a 1. Okay, so P2 plus some term here. Okay, and this term is an integral that is integrated over all points that you are observing in region R2. Okay, so this means that if I can make this integral term negative or less than 0, I mean only this term is negative or less than 0, then you can further minimize the probability of error. Okay. On the other hand, if this term is positive, okay, then your probability of error is increasing. P2 plus some positive term, so it's increasing. So you are observing all the points in R2 and you are trying to make a decision that since they are falling in R2, according to this rule, you are making a decision that a 1 was transmitted. Okay. So if that decision of yours based on the rule that you set here is giving you a term that is negative for this particular integral, then it's further minimizing the probability of error. Okay, so your decision is basically getting an advantage. Okay, so let's say you are taking a decision. That decision is that 1 was transmitted or 1D. Okay, according to this nomenclature. So this is your decision, and this decision is based on the rule that if your received signal falls within R2, then you decide 1. If your received signal falls within R1, then you decide 0. Okay, so this rule is making you to decide that you have a 1 when your point of observation is falling in R2. Okay, so whatever is happening within this integral is based on the points that are all falling within R2, and based on this rule you are deciding that since my points are falling within R2, I am deciding 1. And if your decision makes this integral negative, then if this decision makes this integral makes the integral negative or less than 0, then your probability of error is decreasing. Okay, so that means you are making a right decision because your ultimate target is to minimize this probability of error. So if you are deciding 1 and that is giving this term as negative, then your probability of error is getting reduced further and you are getting advantage. Okay, but if you are deciding 1 and that is making the integral positive, then this term is increasing. Okay, if the integral is positive, then this means your probability of error is increasing. So therefore this decision is not optimum. You have to change your strategy. Okay, so if this is greater than 0 or positive, then your probability of error is increasing. So So in that case, your decision has to be changed. So you cannot decide 1 if this is increasing, because this increasing means the probability of error is getting increased, which you don't want. So you have to change your decision, and you have to make a decision that it was actually 0. So if this term, this integral is negative, then you decide that 1, which is fine based on the fact that you are observing the points on R2. But then if this decision is not giving you an advantage in terms of probability of error, instead it is giving you a disadvantage by making the probability of error increase, then you have to change the decision and you have to change your strategy. So then you decide that a 0 was transmitted. So summarizing this whole concept, we have this term which was inside the integral in your last slide here, p1 f of r given 0 minus p2 f of r given 1. This term, if that is positive, then you decide a 0. If that is negative, then you decide a 1, which we just explained. So if it is less than 0, you decide 1. Like this, you decide 1, and if it is greater, then you decide 0. So this is the optimum decision rule, optimum error probability decision rule. If you decide like this, then your error probability is always getting minimized. So you can write this equivalently as this ratio of the two conditional densities. If this is greater than or equal to p1 over p2, then you decide 1, or otherwise you decide 0. And this ratio is called the likelihood ratio. So the decision rule above, you can see, was derived without any specific knowledge about the statistical properties of the noise. Okay, so now we will see, if we introduce the statistical property of noise, then what will happen. So let's say that the noise has this Gaussian distribution. So from your received signals components, or the observations R1, R2, R3, R4, they are all statistically independent Gaussian random variables, and the variance equal to the noise variance n0 by 2, and the mean for R1 and R2, the mean is Si1 and Si2. Okay, but for the other terms, the mean is 0, and this comes directly from here. So your R1 was this plus W1. W1's mean was 0, because this is a 0 mean random variable, because it is a component of the 0 mean noise. So the R1's mean will be just this. If you take expectation of R1, then this will give you Si1. Okay, if you take expectation of R2, then this will give you Si2. And then if you take the expectation of R3, then this is the expectation of the noise value itself. So this will be 0, everything will be 0 onwards. So so let's say the mean of R1 is Si1 and mean of R2 is Si2, where if I equal to 1, then 0 is transmitted, I equal to 2, 1 is transmitted. And for 3 onwards, the mean is 0. So now I can write, and also these are all statistically independent. So I can write the distribution of the received signal given a 1 was transmitted is a multiplication of all these individual conditional densities. So R has all these components R1, R2, R3, etc., and they are all independent, so you can write them as the product of the different individual PDFs. Okay. Similarly, for this one also you can write this. Okay. So the condition that 1 was transmitted remains everywhere. Okay. And similarly for 0, it is there everywhere. And since R has all these components which are statistically independent Gaussian variables, the distribution the distribution can be written as a product of all these individual distributions. Okay. And out of these individual distributions, only R1 and R2 has means this one. So when we write the PDF of R given 1 was transmitted, so 1 was transmitted means I equal to 2. Okay. If 1 is transmitted, so I can write R1 minus S21 for the first term, this term. So this is the Gaussian distribution for the first term, and first term has R1, and R1's mean is SI1, and since I is 2 because 1 was transmitted, I write S21. Okay. Similarly, for this term R2, we have R2 minus S22, and for the remaining we have not written anything, but just kept this as same. Okay. For this distribution also you can similarly write this, and from R3 onwards you keep it as same, and we keep it as same because from R3 onwards, whether 1 was transmitted or a 0 was transmitted, the distributions are same because these are just zero mean noise distributions. Okay. So if you take the ratio of this and this, then all the terms from R3 onwards will cancel out because these and these are all same. Okay. So the terms Rj given 1t and Rj given 0t are same, and that looks like this for j greater than equal to 3. So therefore they will cancel in the likelihood ratio, and only these terms will remain. So the decision rule can be rewritten as this. Okay. So this if this is greater than or equal to P1 by P2, then you decide 1. If that is less, then you decide 0. Now you can further simplify this expression by taking the logarithm, natural logarithm of both sides, and then you will obtain these polynomial on this side, this polynomial on this side, and then a constant term. Okay. So the simplified decision rule in the presence of zero mean white Gaussian noise is basically this. So you calculate this expression and check whether it is greater than or less than this expression plus this. So now let's say if P1 is equal to P2, or in other words, let's say if the signals are equally likely, then this logarithm terms vanishes because P1 by P2 is 1 and log of that 1 is 0. So then we get a further simplified version like this. Okay. So what is this? If you recall that this term is basically, if you just consider the signals and the received signal as just points on the coordinate space. So let's say this is your phi1, phi2 plane, and let's say this is your S1. Okay. So S1 has two coordinates, S11 and S12. Okay. And let's say this is your R. Okay. And R has two coordinates, R1 and R2. Okay. So if you calculate the distance between R and S1, then this will be basically R1 minus S11 square plus R2 minus S12 square, and then square root of that. Okay. So basically this left hand side is the distance square of the received signal from the signal S1, and similarly this one is the distance square of the received signal from, let's say, S2, which is here. Okay, so ideally what you are doing after all these simplifications, what remains is that your your received signal, if it is close to S1, then you decide that S1 was transmitted. If it is close to S2, then you decide S2 was transmitted. So distance wise, if you check the distance between the received signal from S1 and S2, then whichever is closer, the probability of that being transmitted is more. Okay, so you can see how nicely the time domain signals, if that are represented on signal space, then just by calculating the distance of the received signal from the transmitted signals in the signal space, you can decide that which signal was transmitted based on the minimum distance. So this is a nice revelation. So in this slide actually shows what I just said. So let's say this is your received signal R2, R, which has the components R1 and R2, and then it makes a distance D2 with signal S2 and a distance D1 with signal S1. So in this figure, D1 is greater than D2, so therefore you can decide that S2 was transmitted. Okay, so this is what is said by this equation. So so I'll stop here and I will continue in the next lecture.